Hello everyone, welcome back to another video. Today we're going to continue with our series of cyclic geometry. This forms part of question paper 2 of mathematics, and this is specifically for the November 2022 question paper. We're going to have a look at question 9.2.1 as well as 9.2.2, which focuses on the proving element for cycle geometry. And we're given a statement where we're being told that there is a diagram, as I've tried to draw here. In this diagram, we are told that the points E, B, F, S, and P are falling or are on the circle or the circumference of that circle. And we are told that there are various lines that are in this diagram. But of interest, we're being told that E, T, and TF are being bisected by the line OT. And also we're told that GF is parallel to PS. Those are facts that I think will come in handy with the upcoming questions. So the first question is asking us to prove that OTBG is a cyclic quad. So prove that OTBG is a cyclic quad. So we must prove this. Alright. What is a cyclic quad? So there are two things here. We are being told that there's a cyclic and then there's a quadrilateral. A quadrilateral is a shape that has four sides. We all know that. There is a triangle, three sides, a quadrilateral, four sides. But now when we talk of a cyclic quad, it means that this quadrilateral must fall in a circle. It must be bounded by this circle. Specifically, the points that form these four sides, they must touch the circumference of the circle. Otherwise, if it does not touch the circumference, then it's no longer a cyclic quad, but it is a quadrilateral. So cyclic quad, those things go together. For it to be a cyclic quad, the points of the quadrilateral need to fall within the circle, the circumference of the circle. So if we are being asked to prove that OTBG is indeed a cyclic quad, we must take note of what I've just explained to you. But every time when you're being asked to prove that a certain shape must abide by some certain rules, try to draw out what they want you to prove so that you can at least aid to your solving of the problem. You can sort of have many ideas when trying to attack such questions, because trust me, you do forget at times that they say this is a cyclic quad. How does a cyclic quad look? Or where or how far have I gone with the question? If you try and draw out all your ideas, it will be easy to succeed when it comes to cycle geometry. Now let's try and draw out a cyclic quad. So a cyclic quad, as you see on my green dashes, very roughly drawn. These dots here are trying to draw out what this cyclic quad will look like. So there will be this circle, and then OTBG will have those points OTBG falling or literally lying on the circumference of that circle. We see that O touches that circumference, T touches that, B and G. So we need to prove that indeed that is a cyclic quad. So how does one go about proving that something is a cyclic quad? Well, there are many ways, and I'm going to try to make it easy for you. On a cyclic quad, we have a cyclic quad. It needs to fall. The points of the cyclic quad need to fall on the circle. A cyclic quad, one of the most important things, perhaps not going to mention all kinds of proofs that you can go about to prove that something is a cyclic quad, but these are what is important, I think, on my side, and will definitely, if you have these tools, you will never go wrong with such questions. So for a cyclic quad, the opposite interior angles, this angle is opposite to this one. Those two angles, C and B, if this is A, so let's say C, A, B, C, D. So angle B plus angle D should give you 180. That is a cyclic quad. Cyclic quad has the opposite angles supplementary. So it means that if you had to add those two angles, they should give you 180 degrees. The same applies for A plus C. Those angles need to give you, when you sum them, they need to give you 180 degrees. You should already get an idea now that if you add all angles in a cyclic quad, they should all amount to 360 degrees. Also, another fun fact is that if you are to draw a line such that it continues from B, A, then let's say going to F, the angle formed by this line and that chord AD, this angle is equal to the opposite interior angle. So if you are to have this angle, then this angle has to be the same as that one, which makes sense because this angle plus this one need to form 180 degrees because they are in a straight line. But also we know that this angle plus this angle need to form 180 degrees. So we always know that that one should definitely be equal to that opposite angle. All right, so that's just one of or two of the rules that you can go about to prove that something is a cyclic quad. But the last one, which I find very interesting, is that if you are to draw a cyclic quad, and then you have A, B, C, D. What you must also understand, for a cyclic quad will be something like this, 4 sides. To prove that it is indeed A, B, C, D are indeed a cyclic quad, or those points fall on the circumference of that specific circle, what you need to understand is that there is a theorem that says that for these angles that are subtended by this arc, so arc AB subtends this angle as well as this angle. Those two angles are equal. Same applies to CD, arc CD. These angles, those two angles are equal. And back in the days, me and my friends used to call that theorem the butterfly. So if you have something like that, a structure like that, and you're asked to prove that it is a cyclic quad, remember that theorem. All right, now let's try and attack our question in here. How would we go about proving that indeed OTBG is a cyclic quad? So I'm going to erase this. So keep note of what I've just explained to you. To prove that OTB is a cyclic quad, we need to realize that, okay, if we go about that the theorem that says that the opposite angle, so this angle is opposite this one, they need to sum up to 180. We can go with that rule, but we can already see that it's going to be hard for us because this angle is unknown, this one is unknown, yet this one is unknown and this one is unknown. So it's going to be a problem for us. Or maybe we can go about this one and this one. But this angle is unknown. We can probably find this one quickly, and also these ones are unknown. So we are left off with the other theorem that I said there's a butterfly. So if you notice this circle here, there is this arc. So if we can find this angle, so this angle in here, if we can prove that this angle is equal to that one, then we have a cyclic quad. But it's going to be a little bit difficult. Or we can try and prove that this one here is equal to this one. Maybe that's possible. So let's go about that. For you to prove that, you need to remember some other questions, some other theorems. And like I said to you, we are already given a leeway in that we are told that OT, this line OT bisects EF. So as soon as you're given such a fact, know that you are supposed to use it at some point. So EF is bisected by OT. And if you remember, there's a theorem that says that if a line from center intersects a chord, if it bisects that chord, is going to be perpendicular to that chord. And we all remember that theorem. We normally look at that theorem in terms of the other way around. If a line intersects a chord EF and it is perpendicular to that chord, then we'll know that it bisects the chord. So it can always go the other way around. And definitely now we can prove that. So OT E. So OT bisects EF. So it means this angle and this angle are equal to 90 degrees. So how do we name this angle here? So it's OTE. You can go back to my previous videos about how to name or know this convention of naming angles. So OTE is equal to 90 degrees. And the theorem is that line bisecting chord, so a line from center, so a line from center bisecting chord is perpendicular to chord. So a line from center bisecting the chord has to be perpendicular to that chord. Okay, so we have that angle OTE, and you remember we are still trying to prove that butterfly theorem, that this angle must be equal to this one. So how can we go about finding or proving that indeed angle B is going to be equal to our OTE? So another thing is that we are being told that, we're told in the statement that GP is the tangent to this circle. And we also know that OB is a radius. Remember, a radius that intersects a tangent has to be perpendicular to that tangent. And you might be asking yourself, how is this man figuring out all of these things? I told you that once you are given facts within a diagram, like this being bisected, this line bisecting this one, know that you'll use that. If you are given a radius, just always think of theorems that go about a radius and think, how can I use that to my advantage? If you are given a tangent, think, what theorems go about with the tangent? So we already know that if there's a radius and it's intersecting that line, the tangent, then it's definitely perpendicular to that tangent. So OBG is equal to 90 degrees. Reason being, radius perpendicular to tan. That's the theorem. The radius is perpendicular to tangent. That's the theorem. And please refresh your minds around that theorem. Okay. So we now see that this is 90 degrees and this is 90 degrees. Therefore, OTE is equal to OBG. We can already see that these two are equal. And if those two are equal, therefore OTBG is a cyclic quad. So OTBG is a cyclic quad. So OTBG is a cyclic quad. And what is the reason? The reason is that butterfly theorem. And of course, you won't write butterfly in your answer. We will say that its angles subtended by the same arc. They are equal. So the theorem is that angles subtended by same arc. So that's the theorem. So this is the arc OG and you can specify that the arc I'm talking about is OG. So arc OG is subtending the angles OBG and OTP, and therefore those angles are equal, and that is our cyclic quad. So let's go to the next question. All right, the next question is asking us to prove that angle GOB is equal to angle S. So angle S is this angle right here, is this angle, and then GOB is this angle. All right. Remember, we told that, because now you should ask yourself, now why suddenly we are being asked something about S, and how does S relate to this whole shenanigan that is happening here? So remember that we were told that PS is parallel to GF. Then you're already in your mind thinking, oh, if things are parallel, I should already remember that parallel lines, there's angles, some are equal, some are supplementary, and all those things. So you should remember your alternate angles, you should remember your corresponding angles, and use that to your advantage. We'll cover that. If you want me to cover deep about all the specific angles, so alternate angles, corresponding angles, please indicate in the comment section. So corresponding angles, we need to think about that. Alternate angles, we need to think about that when solving this answer. So we've already proven that OTBG is a cyclic quad. And remember, we proved that through the butterfly theorem. So this angle is equal to that angle. So if this angle is equal to this angle, it means we can also use the butterfly theorem the other way around. We can also locate these two angles. So we already know this angle is equal to this angle. Or we can say this angle is equal to this angle, because these two angles are subtended by this arc, BG. You should ask yourself now, why is this man trying to go that route? Because I already know that if GF is parallel to PS, then we are already knowing that we have an F here. We have an F. This is an F. So on F, this angle is equal to this angle. So we should already know that. So angle S is equal to angle BTG. So angle S is equal to angle BTG. So it's equal to this angle in here. So remember, hopefully you can see this. And the reason is corresponding angles. So corresponding angles. So BTG is equal to angle S, corresponding angles. And I've just told you that we have a butterfly theorem. So this angle is equal to that one. Alright, so angle BOG is equal to the same angle BTG. And the reason behind this angle being this one, I've told you in the previous question that it's because those two angles are lying on or are subtended by the same arc and on a cyclic quad. So angles in a segment. Angles in a segment. That's another reason, or a better way of saying butterfly. You can go and research about that. What is a segment? And but the best way for you to understand is that those two angles are subtended by the same arc and therefore are equal. If indeed OTBG is a cyclic quad. Alright, so if those two angles are equal, this is equal to this, therefore angle S is definitely equal to angle GOB. And that is the conclusion for our questions. Thank you. Please leave any comments or questions in the comment section below. I do understand that this is a tough question, so let's try to unveil it together. Let's make it simpler together. Thank you.